Dear student, let us begin lectures on machine design part 1. This is lecture number 37 and the topic of today's discussion is design of cylinders and pressure vessels. This is part 2 of the lecture. In last lecture, that is in lecture 36, we have learned how to design a pressure vessel when the pressure vessel is modeled as a thin cylinder. Now we knew about two kinds of stresses. One is hoop stress or circumferential stress and another is longitudinal stress. Now designing such pressure vessels, that is designing the proper thickness of such pressure vessel is very important, because if it is not designed properly, then that may lead to a total catastrophe. And there are various codes available. One such code, as I mentioned, is ASME code for boilers and pressure vessels. Now today we shall discuss how to design a cylinder when the cylinder is thick. Now let us see what are the stresses in a thick cylinder. Now I want to remind you that a thick cylinder is a cylinder where the thickness, that is this distance t, is greater than equal to 0.1 of internal diameter di. So if this is satisfied, then we call this cylinder to be a thick cylinder. Now let us look at what are the stresses in such a cylinder. Now if you consider the total cylinder, which has outer diameter, that is, this is dO and this distance is di, and this is subjected to pressure from inside. P is acted over here. Now what will be the stresses? Now in order to find out the stresses, let us look at what are the forces acting on a small element. Now if you increase it, that is zoom this small element, then we see that it looks like here, where this angle is, let us say, delta theta, which is very small, and this radius is r and this is delta r. So this distance will be r plus delta r times delta theta and we want to find out the different forces on that. But before doing that, let me tell you that there are two possibilities. If the cylinder is very small in length, that is, if it is modeled to be a disc, then of course we can assume, and of course the pressure is acting inside or outside, but it is acting throughout the same length. So therefore the stress along the z directions, that is, if we consider this to be xy plane, so the z direction will be the perpendicular to the xy plane, and if the z direction, if the stress along the z directions, then 0, and we call this a plane stress problem. Plane stress problem. Now this is for a very short cylinder. Short cylinder, also for the disc. Now if the cylinder is very long, then we can neglect, except for the small deformations near the end, we can neglect the shear strain throughout. So the shear strain is 0, and in that situation we call it plane strain problem, and this is for long cylinder. Now it is interesting that if we have a cylinder which is subjected to pressure of this kind or maybe pressure from outside, then both the small cylinder and long cylinder, that is both the plane stress and plane strain assumptions will lead to the same result. So therefore, we are considering here the case of plane stress, that is there is no stress along the z directions. Now if this condition is satisfied, now I want to remind that this plane stress and plane strain problems are different if the loading is different type. We shall see in two cases where the plane stress and plane strain problems are different, but for this particular case it is immaterial whether it is in plane stress or plane strain problem, because they are going to lead to the same results. Now let us see what are the forces acting on it. Now here there will be sigma theta, and remember this is axially symmetric problem. So the sigma theta will be same throughout the circumference. So here also we will have sigma theta, the stress. Therefore the total force will be sigma theta times delta r, and suppose this thickness we have taken to be unity. So here this is sigma theta times delta r times unity. So this is the total force. Here the force is again sigma r, and there of course the sigma r will vary. You see here sigma r is minus p, as it is obvious because there is a pressure acting over here. In this phase there is no pressure acting, so therefore sigma r is 0. So therefore a variation of sigma r is expected along the thickness. So therefore sigma r, if we take to this phase, then it will be sigma r plus d sigma r, where this d sigma r is a very small component added to sigma r. Now we are ready to use our statical equilibrium equation. Let us look at that. If we use the statical equilibrium equations, then we get sigma r, and here the total force is sigma r is the stress. So therefore the force is sigma r times r delta theta times 1. So this is the area of cross section, minus sigma r, that is if this is in that direction minus, so it will be plus sigma r plus d sigma r times the length, which is equal to r plus delta r times delta theta. And now here two forces are acting of magnitude sigma theta times delta r times 1, but we are now considering the force balance in the along the radial plane. So therefore only a component will act, and that component is equal to sigma theta delta r times twice sine of delta theta divided by 2, and that must be equal to 0. And if you use this, then what you get is minus sigma r r delta theta plus sigma r r delta theta plus d sigma r r delta theta plus sigma r delta theta, plus there is a term d sigma r delta theta, now which is very small in magnitude, because other terms are of the order of delta theta, delta theta, etc. But delta r times delta theta times delta sigma r, this is really small quantity, so we can neglect that quantity and we can write down this way, that is only those three terms from this expression, and from that expressions comes delta r times sine delta theta by 2, which is equal to delta theta by 2, twice of that, therefore, this is delta theta and that is equal to 0. When you write down this expression in somewhere compact form, then what we get is this result, that is r d sigma r dr plus sigma r minus sigma theta equal to 0. Now, this is the statical equilibrium equations. The other statical equilibrium equation, if you consider along the tangential direction, we have considered only the radial direction. If you consider along the tangential direction, then of course it is trivially 0 as the symmetry implies. So, therefore, this is the only equation which is available. Now, there are two unknowns, sigma r and sigma theta. Of course, these are the two stresses which we are interested in, and there is only one equation. So, therefore, we need to take one more equations, that is more things are required. It is then it's not possible to derive the expression for sigma r and sigma theta based on this equation only. So, we have to consider the kinematics of deformations. Now, this is done if we consider the deformations, and for the deformations for the axis symmetric problem, epsilon theta, which is the strain along the theta direction, this is the theta direction, circumferential directions. The strain along that directions is equal to u by r, where u is the displacement along the radial directions, and sigma r, epsilon r is the radial strain, which is equal to du dr. So, these are the expressions containing sigma del epsilon theta, epsilon r, and now we can combine this epsilon theta and epsilon r with sigma r, etc., by using the Hooke's law, which says that sigma theta is equal to epsilon theta is equal to sigma theta minus nu sigma r divided by E, and epsilon r is equal to sigma r minus nu sigma theta by E. So, these are the four expressions which are required, and when we combine them together, we get one equation in u, in terms of u, that is the displacement of the of any particular point. Now, that equations I am not going to derive, but I give you the end result of it. When we do all these calculations, then we arrived at this following expression, that is sigma r is equal to C1 minus C2 by r square, and sigma theta is equal to C1 plus C2 by r square. So, where C1 and C2 are the constants which are to be determined knowing the boundary conditions. Now, what are the boundary conditions? In this case, where the cylinder is subjected to internal pressure, then of course, the boundary condition is that sigma r is equal to minus p at r equal to ri, the inner radius, and sigma r is 0 at r equal to r 0. So, therefore, if we use this expression first, let us say, then we get C1 minus C2 by r0 square is 0, and if you use this expression, then we get minus p equal to C1 minus C2 by ri square. Now, using these two equations, what we get is the following. That is, C1 will be equal to C2 by r0 square, and minus p equal to C2 1 upon r0 square minus 1 upon Ri square. So when we calculate C1 and C2, so from these expressions we can get C2 in terms of R0 square Ri square divided by R0 square minus Ri square times P, and C1 is this divided by R0 square. So when we use those expressions, then ultimately for that case we get this following relationship, that is sigma r is P times Ri square Ro square divided by Ro square minus Ri square divided by 1 upon R naught square minus 1 upon R square, and sigma theta will be equal to, let me write down sigma theta will be equal to P Ri square R0 square divided by R0 square minus Ri square 1 upon R0 square plus 1 upon R square. So what will be the distribution? You see, at R equal to Ri, this becomes minus P, which is very clear from here. If you substitute here in this expressions Ri, you will get sigma r is minus P. If you substitute here R equal to R0, then you get sigma r is 0. And here if you substitute here R equal to Ri, then what you get is at Ri sigma theta is equal to P Ri square plus Ro square divided by Ro square minus Ri square, and at R equal to Ro, sigma theta will be equal to twice P Ri square divided by Ro square minus Ri square. So that is clear. Now if you represent it graphically, then it looks like these two formula are very important, and we can design the entire cylinder based on these expressions. Now we shall come to that a little later, but for this time being, let us see the distribution of the stresses across the thickness. Let us see what will be the distribution of sigma r. Here we have the cylinder, and this is subjected to internal pressure P from all sides. Here the distribution of sigma r will be, now at Ri, here sigma r is minus P and it goes to 0 in this position. So this is the distribution, and this is always, so this is the distribution of sigma r. And what is the distribution for sigma theta? Sigma theta is distributed little different way. Sigma theta is quite large here. Here this is P times, so it goes to decreases this way. Here this value is P times Ro square plus Ri square divided by Ro square minus Ri square, and here it goes to twice P Ri square divided by Ro square minus Ri square. So these are the stresses. This is sigma theta. So now these are the two kinds of stresses which are there. Now knowing this, we can calculate what will be the shear stress. Now the shear stress will be, as we see, it's a plane stress problem, then the shear stress is defined, tau will be equal to sigma theta minus sigma r divided by 2. This is the maximum shear stress. Now, what will the maximum shear stress at this location will be equal to definitely this minus this one divided by 2, that is sigma r. If you do that, then it becomes the shear stress here at Ri tau max. So, this is tau max will be equal to, if you do that, it becomes P R0 square divided by R0 square minus Ri square. And at R equal to R0, so this is at R equal to Ri, at R equal to R0, tau max will be equal to sigma theta, which is equal to P Ri square divided by R0 square minus Ri square, and sigma r, which is equal to 0. So, therefore, this sigma theta minus sigma r by 2, that gives the result P Ri square divided by R0 square minus Ri square. So, definitely as R0 is larger than Ri, we can say that the shear stress will be the maximum shear stress will be larger at R equal to Ri. So, when we want to design that, then we will have to take this into considerations. Now, how to design the thickness? The problem is that we are given, suppose this value P and Ri, the internal radius. Now, what will be the thickness of the cylinder? So, that will be the next problem, but in order to do that, we must remember what are the different stresses in a thick cylinder. Now, as I said that the stress distribution for sigma r and sigma theta values for the plane stress problem and plane strain problems, they are same, but the design will be different if you go from plane stress to the plane strain problem, as we can see very easily. Now, this is about the stress distribution in a thick cylinder. Now, how to design that? In order to design, we have various equations. One is Lame's equation. Now, probably I mentioned that the derivations which I have done just now is known as Lame's equations, that is sigma r is equal to C1 minus C2 by r square, and sigma theta is equal to C1 plus C2 by r square. So, this is the Lame's equation, and we design the thickness based on this Lame's equations. Now, if the cylinder is open-ended cylinder, then, and of course open-ended cylinder and with ductile material, then what we have, ductile material, then the design criteria is given by Bernoulli's equation, which is a little different, we shall see very soon. If the cylinder is closed-ended and the material is ductile, then it is governed by Clavarino's equation, and for high pressure oil or gas pipe, the design is guided by what is known as Barlow's equations. So, now let us see how to design, how to get the proper thickness of a thick cylinder which is subjected to internal pressure. Now, first one is based on Lame's equation, that is, here this is subjected to internal pressure, and inner radius, let us say r, this one is Ri. Now, how to get Ro? That is, Ro will be equal to Ri plus T. So that is the design criteria. Design problem is to select this T. Now if we say that the material fails under tension, then definitely the maximum tensile stress will occur in the inner surface, and that will be sigma theta. So therefore if it fails in tension, so the case 1 is fails in tension, then of course we have sigma theta. The maximum tensile stress will develop sigma theta at r equal to Ri, which is equal to P times Ro square minus Ri square divided by Ro square, I am sorry, plus here and minus in the denominator. So this is the maximum tensile stress developed, and this must be less than equal to, that is in the design limit, this must be equal to sigma allowable. Then how to make these calculations? That is very simple. So r naught square plus Ri square divided by r naught square minus Ri square is sigma A divided by P. Now if you make this componendo dividendo, then what you get, Ro square divided by Ri square is equal to sigma A plus P divided by sigma A minus P. Now if you use this relationship, that is Ro is equal to Ri plus T, then what you get is R. Now here the next step is just to this one will be equal to that, and if you substitute here Ro to be Ri plus T, then it is very easy to see that T will be equal to sorry, so again T will be equal to Ri times under root sigma A plus P divided by sigma A minus P minus 1. So this is the sorry, this is how one has to design when the material fails in tension. Now for such cylinder, the material may fail also in compressions, but before going to that stage, let us see one thing, that if sigma A, if P is greater than sigma A, then T is not real. So therefore it is not possible to design any cylinder which will sustain a pressure more than the allowable stress. So this is very important, that we cannot design any cylinder using on the single cylinder that will sustain an internal pressure beyond the allowable stress limit, and allowable stress limit is roughly equal to 0.8 of sigma yield strength, and if it is brittle material, is about 1/8 of ultimate stress. So for ductile material this is so, and for brittle material it is 0.125 times sigma u, which is the ultimate strength. Now if that condition is satisfied, that is P is greater than sigma A, then no real value of T is possible and we cannot design any cylinder. So how to avoid that? In the next class we shall learn, if we use another cylinder, then on top of it and press fit, then it can sustain a very large pressure higher than what is sustainable with single cylinder. So this is a case of compound cylinder, and we shall study it in somewhat details in the next class. But for the time being, let us go to the case 2, which is the case when the material, that is, it fails in shear. So, it fails in shear. Then let us see what is the maximum shear force, or what is the maximum shear stress. The tau max, we have seen that maximum shear stress occurs in the inner boundary, and that is equal to P RO square divided by RO square minus RI square. And in order to have a safe design, this must be tau less than tau allowable. So, now how to do that? This is R0 square divided by R0 square minus Ri square is equal to tau allowable divided by P, and if we just subtract it, so then it becomes R0 square divided by, or let us not do that. So, this is R0 square times P is equal to R0 square tau A minus Ri square tau A. Therefore, R0 square by Ri square, from this expressions you can see that this becomes R0 square by Ri square, it becomes tau A divided by tau A minus P. So, then again is the routine matter, we just make R0 by Ri, which is equal to under root of that, and we use this expression, that is R0 is Ri plus T. Then ultimately what we get is the same, this result, that is T will be equal to Ri times under root tau allowable divided by tau allowable minus P minus 1. Again you see that in this case, if pressure is greater than tau allowable, then this material will fail in shear, and we cannot design any cylinder, any single cylinder is incapable of doing of sustaining that high pressure. And tau A is normally taken to be sigma allowable divided by 2. This is the rough estimate, and if you use that, you can get this relationship in terms of sigma allowable, which are coded. So, there are codes available which says what will be those values of sigma allowable. Now, this is the case of design of thick cylinder when it fails in shear. Now, so these are based on the Lame's equation. Lame's equation. Now, let us look at the other conditions, that is when the cylinder is now open ended, then of course the failure criteria is that, and this material is ductile. Remember, when the material is ductile, then the stress strain relationship is somewhat like this, sigma and epsilon. So, the failure criteria is that epsilon is less than some epsilon allowable. So, this is the failure criteria which is used in Bernoulli's equations. Now, what is epsilon? That is the maximum strain, and this is equal to definitely epsilon theta, and you can verify that, and this is equal to this divided by r divided by E. So, 1 upon E times sigma theta is equal to P Ri square Ro square divided by Ro square minus Ri square times 1 upon Ro square plus 1 upon R square minus nu times P Ri square Ro square divided by Ro square minus Ri square 1 upon R naught square minus R square. So this must be lesser than epsilon allowable. Now if one uses that, that is after some simplification, we get the following form, that is this part is constant, this one and that one. So what we get here is this part, let us say P prime, let us denote this as P prime. So P prime divided by E, and it will be 1 plus nu times 1 upon R square plus 1 minus nu times 1 upon R square. So this is the expression, and we see that now there is a term Poisson's ratio appearing here, because we are now considering the maximum strain theory. Now when we do all these calculations, ultimately I shall give you the end result, which of course you may derive, and it comes from this line itself, that the T thickness is given as Ri times under root again here we have that epsilon theta is equal to P prime by E times this one. Now if we take that epsilon theta times E, that is we consider epsilon sigma theta to be epsilon E times epsilon theta, then really limiting this value of epsilon theta is limiting this value of sigma theta prime, and this is normally taken to be the allowable stress limit. So now if you use that, what you get is this form, that is sigma allowable plus 1 minus nu times P divided by sigma allowable minus 1 plus nu times P minus 1. So this is the results from Bernoulli's equations, and this is based on the maximum strain energy, that is the maximum strain within the cylinder. Now this is very important to design a cylinder, a long cylinder which is subjected to internal pressure and which is made of ductile material, but remember that this cylinder is now open ended. Now if we have a closed ended cylinder, then the Clapeyron's equation is used, and that looks little different. Let me explain somewhat here. If we have a closed cylinder, then what we have? So this is the cylinder which is, now this is a thick cylinder, and we have a cap out there. So this is a cap and a cylinder. So now you see, this is no more a plane stress problem. Here we have sigma z. What is the value of sigma z? Sigma z average longitudinal stress is taken to be that is, if you take across a section over here, then what you get, the total force will be equal to, sigma z is governed this way, that is sigma z, let me clear it out. We are interested in finding out the sigma z. Then how to do that? First we take the cart over here, and then write down this equation. There will be sigma z, and pressure is acting throughout. So therefore, if you balance the equation along the vertical directions, which you get is P times pi Ri square is equal to sigma z times pi rho square minus ri square. So, this is equal to this gives sigma z equal to p times ri square divided by rho square minus ri square. So, this is the expression for sigma z. Now, if the material is ductile, we can use the same principle, that is the principle of maximum strain, and in that case the strain looks different from the previous one because we have to consider again sigma z, but in this let us see how does the strain expression look like. Epsilon theta, which is the maximum strain along the circumferential directions, and this will be the maximum strain which you can verify, is equal to sigma theta minus nu sigma r minus nu sigma z divided by E. Now, remember, and the maximum strain will be in the inner surface, and here sigma theta is equal to P times r I square plus r o square divided by r o square minus r I square. Sigma r is equal to minus P, and f sigma z is given this way, that is sigma z is equal to P times r I square divided by r o square minus r I square. Now, if you use all these expressions, then the next step is to insert these three expressions here in this expression for strain, and noting that E times, that is Young's modulus times epsilon theta, gives somewhat an estimate of the stress along the circumferential directions, and limiting the sigma epsilon theta is just limiting that value of the stress, and that stress is taken to be the fracture stress or the tensile allowable stress of the material. So, if you use all these things, then after making all such calculations, you get the following expression, that is T will be equal to Ri times under root sigma allowable plus 1 minus 2 nu. Earlier it was 1 minus nu, now this is 1 minus 2 nu plus P divided by sigma allowable minus 1 plus nu times P minus 1. So, this is the result obtained for Clapeyron's equation, and this is valid for closed ended cylinder. Again, these are the three expressions which are normally used while designing it, but if we want to design the pipe for a very high pressure, then sometimes we use the hoop stress formula, that is the same expression for the thin cylinder, but instead of taking the average diameter, we take the outside diameter. That is, now we see what will be the thickness for a high pressure. So, pipes carrying high pressure oil or gas. In that case, remember the design criteria for thin pipes, thin cylinders, was that sigma theta was PR by T, where earlier case R was the mean diameter for a thin cylinder, which is equal to the average of the outside diameter and the inside diameter. But when we want to calculate for the thick cylinder, in these expressions we put, instead of r, we put r0. Definitely the value is the maximum over here, sigma theta, and this must be lesser than sigma allowable. Now this is the design condition from which the value of T is calculated. Again, depending upon the nature of the liquid it carries, we have to give some allowances as like the thin cylinders. So these are the ways, few ways of designing a thick cylinder. Now remember, we have used Lamè's equation. Lamè's equation is based on the principle that the stress, the material fails when the stress, normal stress exceeds a certain limit, sigma allowable. Also we may use that the material fails when the shear stress gets a maximum limit. Now these are based on Lamè's equation. In Bernoulli's equation, this is valid for an open cylinder, and here the design criteria is that the strain, that is the circumferential strain, which is of course larger than the radial strain, the circumferential strain reaches an upper limit, and with this expression we calculate the Bernoulli's equation, the thickness using Bernoulli's equations. Clapeyron's equation uses the same principle. Now it is applied for a cylinder which is closed ended. And lastly, we calculate the thickness of a pipe which carries high pressurized oil or gas using a very similar familiar looking formula used for calculating the thickness in the thin cylinders. The difference being, here instead of taking the mean radius, we take the outside radius. So this is how these things are calculated. Now let us come to stresses in a rotating disc, rotating thick cylinder. Now how this is important? We see, we have also talked about how to design a flange, which of course the purpose of the flange is that it connects to shafts and the shafts rotate. So therefore along with the shaft, the connections, the flanges also rotate, and the stresses developed in that flange. Then in this case, when we want to find out the stress, we have to differentiate between the plane stress problem and plane strain problem. Now plane stress is for short cylinder disc or for short cylinder and plane strain is for long cylinder. Now how to calculate the stresses? Then we revert back to the same procedure, just by first finding out the equilibrium equation. Now if you consider again a very small element, as we have done for a thick cylinder, then it looks like again the same stress, sigma theta, sigma r plus d sigma r. In addition, here there will be one force which acts along the radial, that is the centrifugal force, because now the entire thing is rotating with omega. So therefore again there will be another force which has the magnitude, this is the entire mass of it. The force is now the mass delta dm and omega square r, and dm is mass as before is the total volume times the density, rho is the density of this material, let us say, and the total volume is delta r times r delta theta times unity. As before, we take the thickness to be unity. We consider here in the plane stress problem. So we take unity thickness because in the axial direction there is no stress. So this is the total mass, and if you write down this equation, again the static equilibrium equation, just by balancing the force at different along the radial directions, then what you get is that very similar expressions, that is r d sigma r dr plus sigma r minus sigma theta, and plus here we have omega rho omega square r square. This is equal to 0. Now for the plane stress problem, again we will have to find out the expression of epsilon theta in terms of u, which is equal to u by r. Epsilon r is du dr, and then we calculate, we use the Hooke's law. After that we use Hooke's law, that is epsilon theta is sigma theta minus nu sigma r by E, and so on and so forth. Ultimately, when we solve these expressions, we get the following results. That is, now we solve everything, and I shall write down the final form of these expressions. Sigma theta will be equal to sigma r is first 3 plus nu divided by 8 rho omega square r square plus C1 minus C2 by r square, and sigma theta is minus 1 plus 3 nu by 8 rho omega square r square plus C1 plus C2 by r square. Again, this is for the plane stress problem. For the plane strain problem, again it looks different, but I am not going to that details. So now you see the stress develops because of the rotation, and that may limit the speed of the flange, because the maximum rotating speed of the flange may get limited by this sigma theta or sigma r, whatever it may be. So these are the stresses for a rotating thick cylinder. Then we come to the last case, that is the thermal stresses in a thick cylinder, which I shall tell you briefly. The procedure, everything is same. First we write down this expression sigma r dr plus, this comes from the balance equations. Then we write down epsilon theta is u by r and epsilon r is du d theta. But now you see the Hooke's law changes. Epsilon theta is sigma theta minus nu sigma r by E, but here we get alpha T, which is the temperature distribution. Now what is so important, because it carries, say the cylinder carries a liquid which is at very high temperature. Now definitely the temperature will vary from inner surface to outer surface. So this variation can be found out by heat transfer methods, by equations or considering the heat transfer. So these kinds of expressions are now used, and ultimately what result we get is that epsilon theta, say first of all epsilon r, sigma r is equal to minus, here r t is a function of r dr times alpha E divided by r square plus C1 minus C2 by r square, and sigma theta is equal to again r t is a function of r dr times alpha E by r square minus alpha E t plus C1 plus C2 by r square. Again you see, because of the temperature changes, a thermal stress is developed. So all these are very important aspects for designing. Now let us sum up what we have learned today. We have learned how to calculate the thickness of the thick cylinder if it is subject to internal pressures. There are different procedures using Lames equations, Werner's equations, Clapeyron's equations, or for just like the Hoops stress formula. And also we have learned how to get the stresses for when the cylinder is rotating. We also calculated the thermal stresses, that is, if it is subjected to internal thermal, that is the temperature distribution is there, then the stress is developed. So all these things are to be considered properly when we want to design a thick pressure vessel which is containing fluid at a very high temperature. Sometimes it may rotate, sometimes it may not, but that depends upon the system to system. So we come to the end of this lecture. Thank you very much for today. Let us begin lectures on machine design part 1. This is lecture number 38 and the topic is design of cylinders and pressure vessels. This is the part 3 and the concluding part of the lectures on the same topic. Now in last two lectures we have discussed how to design a cylinder when the cylinder is modeled to be a thick one or a thin one, and also we have discussed how to take care of the effect when the cylinder rotates, also the temperature distributions. Just before going further, let us recapitulate once again what we have learned so far in a very brief while. So let us, for this time being, let us again go back to the earlier discussions and just refresh our memories about the stresses in cylinders. Now the discussion started with the different kinds of cylinders. You see, the cylinders are classified according to the thickness and so this is the thickness and the inner diameter di. So it is divided, if this is d, t by